the yes button.
Okay.
But it was kind of like a spur of the moment thing since the person that was supposed to be there didn't show up.
Okay.
It was a few weeks ago.
Did it not show up on your extra credit?
It did not.
Okay, shoot me an email
Gotcha.
and tell me that, and I will record it. Thank you. All right, so nice job on the presentations yesterday. Saw lots of cool projects, lots of good progress from where things started in September, which is exciting to see. So any sort of thoughts, reflections, comments?
I feel behind.
You feel behind?
Yeah.
Relative to where you wanted to be, or relative to other people?
Relative to some other people.
Oh, well.
What are you saying next to Malcolm?
Yes.
I didn't. Oh, well, I mean, Malcolm's been working on that.
Yeah.
For a year, yeah.
That's what I was going to say. Some people, even if they started their SLP in September, it may be something that's been going in their brains for a while, or it may be a branch off from something they've been working on.
I mean, I've played Super Smash Bros. On a Raspberry Pi, so that's what
Yeah, yeah.
makes me feel behind.
I don't have a truth.
But yeah.
Yeah, I thought there's some cool ideas, a lot of creativity. And I think it can be unnerving to sort of talk to people about stuff at first, but at some point it actually starts to get to be kind of fun. Because you realize you're kind of talking to yourself also. You're sort of figuring things out about what you're doing. And that's a really valuable experience, I think. And, you know, inevitably throughout your lives, you're going to be pitching things to people one way or another, right? Whether it's to, you know, work on a project, or get funding for some research you want to do, or, you know, you're trying to start a band and talk somebody into producing your record or whatever, right? Being able to sort of like formulate a vision in your head and then convey it to somebody is a really powerful thing. It's useful in a lot of different areas. So hopefully that was a good experience, or not a horrible experience. And hopefully it left you with some sort of sense of where you're going from here, continuing with your SLP. So this is a component in 222 winter and 223 in spring. So if you're going to be here for the remaining quarters of the sequence, you'll be continuing this process. If you feel like, you know, after a few months of working on your project, this isn't really the project you wanted to be working on, right? Let's talk about it and let's make adjustments, so that hopefully this is something that you're feeling fairly passionate about, right? Something you can really kind of like enjoy spending time and energy on. So let me know if you've got concerns about that.
Maybe I should switch it up and make a website.
Lots of features. All right. So I wanted to talk about some things that we've kind of skipped over. These are not things I'm going to put on the exam, but just some topics that that I had planned to come back to along the way, and I guess this is along the way here. So these are things that will be good to know about in general, living and working in a Unix environment. So the first thing is this business of links. And a link is kind of like a shortcut. Windows calls them shortcuts. It's a way to have something that refers to something else.
Yeah, screen is still.
Thank you. So a link is a way to have a file that refers to another file. And there's various reasons why we might do this. But let's look at some examples. So I have a file here called file name. It's not a terribly interesting file. But there it is. So the first thing we can do is we can create what's called a symbolic link. And we do this with the ln command. That's short for link. Bless you. So the way we create a symbolic link, ln, it takes a switch -s. and then we list the original file, and then we list the name of the new file. And this is going to create a new file which will refer to this original file. So for example, I can say ln-s file name my copy. And now if I cat my copy, it looks like the original file.
What happens if you VI it?
So if I VI my copy, I'm editing this original file. So let me go ahead and fix my typo, and let me make that uppercase. So I edited my copy, but if I look at file name, those edits have appeared in there also. So my copy is really a reference to file name, and file name is the thing that my copy refers to. So if I edit file name, and I add hello a few more times, and I look at my copy, it's got those changes in there. Okay, my copy is a symbolic link to file name. Now if I do an ls-l, this becomes apparent, because my copy shows up with this little arrow after it and then file name. It's a pointer in some sense, not a C-type pointer, but it's a pointer to this other file. I'm playing with a new mouse because my mouse finally bit it. And if I remove file name and I try to edit my copy, it's a new file. Right? It's still there. It's still saying it refers to file name, but if I try to cat it, it'll say no such file. And it's not that my copy doesn't exist, but my copy is just a reference to this thing called file name, and file name does not exist. Now if I make a new file called file name, and then I cat my copy, it refers to file name again. So it's a symbolic link in the sense that file name is referring to another name, right? File name in this case.
Can you put my copy in different directories?
Mm-hmm. So let me go into my home directory. And let me make a link called haha. And haha refers to HomeNIC files, blah, blah, blah. And that's one of the sort of main features that we like symbolic links for, is we can use them to refer to things in other directories or possibly on a different physical device. Right, I can pop a flash drive in and it'll show up as /media/nic/ blah blah blah, and I can have a link to a file on there. And it's symbolic, it's really just referring to this particular name. So if I change the name of my links directory to something else, haha will no longer point to anything valid.
Can you make copies of links?
Mm-hmm. So if I copy haha to haha2, haha2 is now just a plain old file, because what did I say? I said copy this big long thing to haha2. And if I remove haha2, that doesn't affect the original file. And if I remove haha, that doesn't affect the original file. And it doesn't affect this link. So symbolic links, just think shortcuts. Just something pointing to something else, basically. And so, for example, on the Linux server, let's say you're down in your subdirectory and you're working on PA4, and you want to, ingest War and Peace, and it's /temp/War and Peace. And you don't want to keep saying /temp/War and Peace, so maybe you copy it over to your local directory, right? And now you have your own copy of War and Peace. That's great. It takes a little bit of disk space because you're making a new copy of it, right? What you could do instead is make a symbolic link. So WNP refers to /temp/War and Peace. And I could say PA4 less than WNP, and it'll read from the War and Peace file. And then if I came along and I changed the contents of /temp/War and Peace, I added more stuff to it, now your WNP would include that more stuff. And then if I delete /temp/War and Peace, your WNP doesn't refer to anything. Thank you, thank you. All right, so those are symbolic links, and that's mostly what we do is symbolic links. They're quick, they're small, and they work across devices. But there's another version of a link we can make which is called a hard link. And it's exactly the same except we leave off the -s, the symbolic option. So original one and then the name of the link you're trying to create. So now this file hard is a hard link to file name. So here's the contents of hard. Here's the contents of file name. If I change file name, then hard changes. Right, it matches file name. And my copy changes also. So we have three things here that are all sort of referring to the same thing. Okay, suppose I change the name of file name to was file name. My copy, that's a broken link now. My hard link, that's still valid. It's a link to the actual file. So symbolic links are really just linked by name. When I say my copy, I mean FILENAME, or /temp/War and Peace. When you do a hard link, I'm actually saying I want hard to be the same file as file name. And when you rename a file, it doesn't actually change where the file is on disk, so it's still the same file, it just has a different name. And so hard still refers to it. So if you do a -I switch on LS, you get this number in the beginning, it's 9 million something. This is called the inode number. So an inode is an internal representation of each file on the system. And picture a huge array with 9 million entries in it. And if you look at entry 9,311,359, you're going to find information about this thing called was file name. Well, when I try to access the file hard, it has the exact same inode number, which means it's referring to the same file on the hard drive. So these inode numbers are basically how you get from something in your directory, a file name, to the actual contents of the file. So the file is stored as a bunch of bytes on, a spinning platter or a flash drive or an SSD drive or something. And to locate that information, it starts with the inode number. And the inode number lets you look up information about where this thing is physically stored, along with information about its permission and when it was created and so on and so forth. So a hard link creates a new file with the same inode number, basically. And so if I remove that original file, the link that I made is still there. Why? Because it's just a name referring to that inode number. Let me get rid of my copy. So now I have 6 files in my directory, and they're all exactly the same file. Why? They have different names, but when you try to do anything with this file, the first thing that happens is the code will say, what's the inode number? 9311359, and it will go ahead and it'll start doing things based on that inode number. Since they all refer to the same inode, they all refer to the same file. In most senses, they are the same file.
Can you do something like that with directories?
Yeah, you can do symbolic links on directories. Okay, so you can make a directory that refers to another directory. I don't think you can do a hard. I've never tried this. Yeah, hard link not allowed for directory. But symbolically, well, let's make a link to this directory. And let's put it in my home directory called quick. So now I'm sitting in my home directory, and I have a directory called quick, and it says quick refers to dot. So if I cd into quick, I'm just sitting in my quick directory. Okay, now I'm sitting in my home directory and I have a symbolic link quick, which refers to this directory we've been working in under links. So if I say ls quick, it shows me what's in that directory.
So would that change, like if you had different files in that directory, would that?
Yeah, it's really just referring to that directory by name.
Perfect.
So in different directories, you can have the same, or you can have files that have the same name, right?
Yes.
So what happens if you create a link to one of those files and then pull it outside of?
You can break the link,
Whoa.
right? So if you're referring to something and you move the target so that your link's not referring to something that exists anymore, it'll just say no such file.
Or if there's more than one that exists, like if you have a.
If you're referring to a target, it's got a path and a file name, right? Or a directory, if it's a directory. But that's unique or it doesn't exist.
Okay.
But here's something you can do. You can make a loop to yourself. So loop is a reference to loop. So if I try to cat that, well, when I say cat loop, it's going to say, well, this is a reference to the file loop, so I really want to look at loop. And it'll look at loop and say, well, that's a reference to loop. So it'll try and look at loop, and it'll say, well, that's a reference to loop, right? And it's going to chase its tail, and it'll notice once it spins around too many times. But sometimes links can get you tripped up like this. I don't know if I can do this. Let's try. And still thinks I'm in quick. Okay, so I have a directory here called whoops, which basically refers to my parent directory. I misspelled whoops. You can move links. Right, sometimes they're just files and sometimes they're the thing that you're referring to. That's a little weird. So I have this file of whoops that refers to the directory above me. Okay, smart enough. What can happen sometimes with some commands is if you have a command that's going to recurse into subdirectories, it would start working on this stuff. It would recurse into this subdirectory, and that subdirectory will refer back to the original directory. And if it's just following links, right, it'll say, well, here's a subdirectory, let's go in there, and it will look in there and say, oh, there's a subdirectory called sub. And it'll look in there and say there's a subdirectory called sub, and so on and so forth. Kind of like I can keep changing into my subdirectory. Right, but I'm not really going anywhere. I'm just kind of running in circles. Even though it looks like I've gone down a whole bunch of subdirectories, right? I'm just in my plain old subdirectory. And that's my parent. So these can get a little quirky sometimes. Don't play with them late at night, unless it's that kind of party. All right, so back to Hardlinks. Let me get rid of this weird subdirectories. I gotta be careful about that. I'm really curious now. Really curious if I forcibly remove sub, if it's going to remove everything in my links directory. Oh, okay, good. All right, so back to hard links. Hard links are simpler in a lot of ways to understand. Hard links are just references to an inode number, right? So these 6 file names, A, B, C, D, E, and hard, are all the same file. Okay, I can edit one, and it will edit all of them. I can rename one, and it just changes the name. It doesn't change the inode number, so it's still a reference to the same file. What's interesting is if I remove one of these, the other files are still there, and they're still intact. So we think that the rm command removes a file from the hard drive, right? But it doesn't. What it really does is it removes a reference to an inode, and then it checks to see if anything else is referring to that inode. So this file, this inode 1359, has a reference count associated with it that right now is saying there's 5 files somewhere that are referring to this inode. And so when I remove E, it says, okay, that's the inode number. It removes the reference E from the directory. And then it says, is there anything else referring to that inode? Well, there were 5 things. I just removed 1. It knows there's still 4 things referring to it. So it's not actually removed from the hard drive, and all of the stuff that's in there is still available. So RM doesn't necessarily delete something from the drive. It only deletes it if you actually remove the last reference to it. I don't know how much of that this goes into.
So yeah.
Yeah, they don't go into that.
Up at the top, it said that it unlinks the file.
Oh, okay.
So under options,
Options, remove, unlink the files. Okay,
and
cool.
then towards the bottom, it says something about may be able to recover contents.
Yeah, so this is a second issue. So right now we've got 4 references to this. I can remove 3 of those, and I've still got 1 reference. So this is still intact. If I say remove D, right, that was the last thing referring to inode 93.11.359. I don't have any way to access that information anymore, the contents of that file. I've removed my reference to it. But chances are that information is still written on the disk. Right? So remove doesn't usually actually remove anything from the disk. And remember, there's no way to remove something from something digital. There's no way to empty a register on the PIC processor. There's no way to clear a variable so it doesn't contain anything. If you have an integer I and it's 32 bits, those 32 bits have 1s and 0s in them. We may not know what those bit values are, but there's always some bits associated with those. This comes down to hardware. If you have a flip-flop, a 7474, and you apply power and ground to it, it has either a 1 or a 0 coming out of the Q output. Guaranteed. Well, almost guaranteed. It's got some value, right? There's no such thing as an uninitialized variable in some sense. There's just variables we haven't initialized. So there's no such thing as an empty spot on a hard drive that doesn't contain anything. It contains something, some pattern of 1s and 0s. And if this particular area associated with that inode number contained, you know, I'm back, ha ha ha, and we remove D, we delete the reference to that, chances are that spot on the hard drive still contains those characters, which means you can undelete, theoretically. So I just created a new file called N, and it's got a different inode number. It's 9311338. That's interesting. It's close to 359. There's 341. There's 359. So now I've created a new file, N3, 9311359. That's the same inode number that we had before. Well, when I created this file, it said make an empty length file because I created it with the touch command. So now if I were to look in that location on the hard drive, some of my data's probably been lost. But you know, some of it's probably still there. Now if I write a bunch of stuff into N3, that's going to potentially overwrite where this original file was, and then my data may be overwritten. But simply deleting a file usually doesn't remove the contents from the hard drive. It just removes the reference to it. So if you accidentally delete a file, usually you can find undelete utilities that will do things like go through and look for things that look like, for example, image files, like JPEG files. You can tell it's a JPEG from looking at the beginning of it, and it'll look for things that have been marked as deleted, and it'll undelete them for you. Or if you know the inode number, maybe you can go back and recreate it. So if you really want to get rid of something, you can shred it. So most decent operating systems have shred utilities built in that will not only remove the reference to a file, but will repeatedly overwrite the contents of the file with something to try to obscure what the original contents were. And this is a tricky thing to do. Simply overwriting it with a bunch of spaces doesn't really delete it, because your hard drive is not a perfect digital device, it's a physical analog device. Which means if you have a bunch of information stored and now you write a bunch of, say, null terminators on top, you're not going to look at it and see perfect zeros written into every bit. You're going to see something that looks mostly like a 0, but not exact. Close enough to 0 that when we treat it as a binary value, we're going to say, yeah, this is a 0, not a 1. But if there was a 1 stored somewhere and now you write a 0 to it, it doesn't look exactly the same as if there was a 0 and you wrote a 0 to it. Right? So this is kind of like when you write something on a piece of paper and then you erase it. Right? Have you really deleted the information? Well, no. If you take that piece of paper, you can see an impression that was left by the pencil. Right? And if you take another pencil and rub it sideways, you can lift the image. Kind of the same thing with hard drives, or with anything physical, for the most part. Right? Everything affects everything else, and so as soon as you write a bit somewhere, you know, that affects the whole universe in some way. And so removing the effect of that is a daunting task. And people with proper motivation can go into a hard drive and do a great deal of work in restoring the contents of it. Even if you've written gibberish on top of this file 20 times to try to obscure it, there's a chance you can go back and you can recover a lot of that original information. So hard drives are interesting, and it's not just hard drives, flash drives, it's memory, it's all this stuff. But shredding helps, right? You just got to be less interesting than someone else to have security.
I guess you'll have to plug the hard drive and break it yourself.
Yeah. And hard drives are fun to take. Next time you upgrade a hard drive, they're fun to take apart. They're pretty amazing devices.
I have one in my car right now.
Oh, cool! Yeah.
Let's go experiment.
Let's get the hacksaw.
Yeah, can I put it in?
Yeah, totally.
My friend turned one into a coaster.
Yeah.
He like took off the casing so you can see inside.
Awesome. Yeah, they're very cool to play with. Yeah, bring it in sometime. We'll mess with it.
Oh, okay.
Okay.
I want to use it.
Oh, you want to use it?
Yeah.
Oh. Once you open the case, they're kind of ruined.
Oh.
Sometimes they have like inert gases inside, so you don't have to deal with air particles. And so if you break the seal, then it's kind of all bets off.
Yeah, they got some mustard gas in there or something.
Yeah, that too. But I mean, think of a 8 terabyte hard drive, right? So how big is Tera?
A lot. Like a bigger gig.
Yeah, it's bigger than. Well, how big is Giga?
Bigger than Mega.
Okay, how big is Mega? We know how big Mega is, right?
Bigger than Kilo?
How big is Kilo?
1,000.
Kilo is 1,000. Okay, so Mega is 1,000,000. Gig is 1,000,000,000. Tera is 1,000,000,000,000.
Peta.
Peta is 10 to the 15th. I don't know the name for it. It gets into the skrillion range. But yeah, so 1 trillion times 8 bytes, so 64 trillion bits. Okay, each bit is a little magnetic dipole sitting on a piece of metal that's spinning around 120 times per second in this tiny little unit.
Yottabyte.
Right? It's what?
Yottabyte.
A yottabyte, cool. HDMI. Yeah, so 64 trillion little individual magnetic dipoles, each of which we can address individually. That's like phenomenal. It's totally crazy. And you know, it's $200 at Best Buy. So hard drive technology is pretty amazing. My architecture professor at Utah said that Silicon Valley should really be called Ferric Valley, because it's really the hard drive industry that's the big money maker, or at least it used to be. All right, so that's a bit of the lowdown on links. And like I say, I'm not going to put that on the exam, but they're useful to know about, and they're useful to utilize sometimes. Let me talk about something bashy. Shred bashing. So we know about the read command in bash, right? We can say read variable name, it'll read from standard in and assign what it reads to a variable. So we can read into a variable called temp, and then we can echo the value of temp like that. So if I run this and I type something in, then that becomes the value of this variable. And if I redirect from standard in, then it'll read from, if I redirect standard in from a file, it'll read from that file, right? So we know how to use the read command. What we don't necessarily know is how we can actually ingest from a file inside a script, right? Read always reads from standard in. From outside, we can redirect standard in with a pipe or with back quotes or with a less than sign. But if we want to actually read from a file inside a script, we need a way to do that, and there's a really simple construct for doing that. So let's read from a file. So we make a while loop, and we say while read variable name do, and then we can, do whatever we want with each line that we read. So we can say the next line is and let's just put it in brackets, make it look cool. And then we can say done to end the while loop, and you can say done less than, you can put in the name of a file. So let's just call it data.txt. So while read variable name do, and each time through this variable will be given the next line of input from whatever this file name is that we specify on the done line. So let's make a data file. So there's our data file. So if I run this, right, it ingests from that file instead of standard in.
Is that how you do PA4 with bash?
That's how you could do PA4 with bash. Yeah, you could make a start at it like that.
Change every punctuation to a new line?
Yeah, you could do that. You could set it to break it into phrases like that. You still need to tally it, but you can do that. And bash has associative arrays just like awk, which is something we didn't get to either. But we'll talk about associative arrays next term. All right, so that's a useful construct to know also. All right, we got 6 minutes. I'm not going to get through what I wanted to get through, so let me just introduce this. We were talking about processes last week, and we know we can use the fork call to create a new process. And we left with this question of how do we communicate between processes. So after you call fork, you can look at the return value, and you can tell if you're the original process or the child process. Right? Child has a return of 0. Parent gets a return, which is the child's process ID. But we'd like to be able to communicate between the original process and the child. And how do you do that? Well, one way to communicate between processes is files. Right? You could simply create a file, and anytime the parent wants to send a message to the child, it simply makes a file with a given name containing whatever the message is. And the child can just continually check to see if this file exists. And when the file pops up, it'll read it, and there's a message from the parent. And you can have another file that the child will create to send a message back to the parent. And that's kind of clunky, but it works. This was how we used to make bulletin boards back in the 70s, because we didn't have, networking and sockets and things like that. But you could use files to do this yourself. And we can do more sophisticated things that are basically embellishments on the same idea of just making a file and dropping things into it. So one thing we can do in Unix is we can use a pipe. And we know about pipes, the vertical bars that connect two commands, but there's actually a function called pipe. And it's a chapter 2 function, which means it's fairly low level. And we can call pipe, and it will create a pipe for us. Well, you call pipe and you pass it the address of a 2-element integer array, and it basically populates that array with 2 numbers.
I missed an L in include.
I'm going to miss a bunch of stuff. Thank you. That'll help. So let's see if we can get away with this. I probably missed an include somewhere. Uni-standard. Let's just call pipe and let's see what it prints out for the value of results. So results 0 is 3, results 1 is 4. And if I call this again inside, then results 0 will be 5 and results 1 will be 6. Okay, that doesn't look very exciting, but it actually is. Because when I call pipe, here's what's happening. The system is creating a communication channel called a pipe. And results bracket 0, which remember it's set equal to 3, and results bracket 1, which it's set equal to 4, can be used to refer to the 2 ends of this communication channel. And the way the channel is set up is you can read from this end and you can write into that end. And if you write something into this file descriptor referred to as a 4, and then you read from file descriptor 3, you'll read whatever was written in. And it doesn't matter who writes it. So I can actually have a parent process and a child process. As long as this pipe is created before the child appears, the child will have the same information that the parent has, and the child can write into this end of the pipe, and the parent can read from that end. And then you make another call to pipe, and you create another pipeline, which the parent can write into and the child can read from, and now you've got 2-way communication.
Is it still 3 and 4? Or is that 5 and 6?
This would be 5 and 6. And then, if you really want to go crazy in the last 35 seconds, there's another function we can use called dupe2, which lets us reassign these file numbers. So this file number 0 is synonymous with standard in. 1 is synonymous with standard out. 2 is synonymous with standard error. This is why you do 2 greater than dev null. It means send standard error out. So what I can do is I can use dupe2, and I can say as the child, you know what, I want to take standard out and I want to reassign it to be file number 4. And now in the child process, anything that would appear on standard out gets shoved into this pipeline, and the parent can read it from here. And it can say I want to take standard in and I want to associate that with file 5, and now anything coming in this pipe will feed standard in on this process. So you can re-hook up standard in and standard out on a process to the ends of this pipeline. And now the parent can basically control this child process because it has direct access to standard in, standard out. That's basically how you would make a server that does Unixy things on another process. All right, but we are way out of time for that, so that's just for your own information. We will start talking about, I posted a study guide on Canvas already. Take a look at that, bring questions, we'll start going through that tomorrow.